last speaker is Professor Dominik Stöckinger from Technische Universität, Dresden. The title is Standard Model and BSM Predictions of MW using different renormalization schemes, FlexibleSUSY implementation, and the example of the MRSSM. Please begin.
Thank you very much, Jeon, for this kind invitation, and sorry for being late for the workshop. I didn't manage to participate in all the talks, but I watched a few of them in the morning here. So thanks also for reading out this three-line, very long title. The talk is going to be a little bit less phenomenological than the previous ones. It has maybe a little bit more basic structure and basic topic. It's more calculational. And our goal that we pursued with this group of people that you see here in the bottom is the following. So we have this spectrum generator, FlexibleSUSY, which also goes back to Jeon's effort. And in this spectrum generator, we wanted to implement a prediction of the W boson mass, which should be as precise as possible and also as model independent and as general as possible. So FlexibleSUSY should not only be applicable to the MSSM or other simple, well-known beyond the standard model scenarios, but it should be as general as possible. So while we were implementing this W mass calculation, we encountered some subtleties and some problems and difficulties. They turned out to have been around in the community already for many years, but had gone unnoticed. And so in order to understand and go to the bottom of it and to solve it and to find a suitable implementation in FlexibleSUSY, really had to go back to the standard model theory and to study the impact of all these different renormalization schemes and how they manifest themselves when we do BSM calculations. That is where the renormalization scheme title comes from. So the outline of the talk is this. I will therefore start with a quite long introduction on the standard model calculation and standard model theory of the W boson mass prediction. This is really a review, and I apologize to the many experts in the audience who are, of course, very familiar with this, but nevertheless, this is important to understand the issue. Then I will present you basically BSM calculations in general terms, and then tell you what the problem is. It's a non-decoupling issue of fake two-loop terms which arise in if you set up the calculation in an, let's say, unoptimal way. And then I present you the solution that we implemented finally. And as just one example, I will present you the prediction of the MW in one specific model, namely the R-symmetric supersymmetric standard model, which is a particularly nice variation of the MSSM, where the W mass can be particularly well compatible with a recent CDF measurement. Okay, so let us begin. The muon lifetime is extremely well measured, and in theory, we can predict the muon lifetime as a function of the W boson mass and many other quantities, and therefore indirectly we obtain a prediction of the W boson mass in terms of the measured muon lifetime. And so the Feynman diagrams that we have here are muon-decay Feynman diagrams where internally there could be loops from standard model particles and also from BSM particles, and in this way we get a shift in the W mass prediction from BSM physics because really what changes is the prediction for muon-decay as a function of the W mass. So technically, the muon lifetime is typically expressed in terms of the muon-decay constant Gmu, or the Fermi constant, which is the effective matrix element or the effective for fermion coupling. And there is simply a standard theory relationship coming from phase space integration and so on, that the inverse muon lifetime is given by this Fermi constant square times a known quantity, which is model independent, and this defines the muon-decay constant Gmu, and this is the quantity which you always see in the particle data book and which is known to extremely high precision. So in the standard model, there is one tree-level Feynman diagram for muon-decay, which depends on the W boson and the vertices between the W and leptons, and therefore the tree-level Feynman diagram gives rise to the tree-level value of the Fermi constant in the standard model, and this is given by alpha, the fine structure constant times pi divided by square root of 2 times the W mass square times the weak mixing angle square. Okay, so this is the basis of the whole theory. Good. So now let me discuss standard model higher order calculations in two different renormalization schemes, namely the on-shell schemes and afterwards the MSbar scheme. So in the on-shell scheme, we first have to fix what we mean by the input parameters. And in the on-shell scheme, alpha is defined via atomic physics, low energy physics, 1/137, and so on. The W and Z masses are defined as pole masses that you see in experiment. And the weak mixing angle is defined just as an abbreviation of this mass relation 1 minus Mw over Mz square. So the weak mixing angle here is not defined via gauge couplings, but via the masses. Then the central relation for Muon-decay and the W mass is given in the box. It contains the tree-level expression times 1 plus delta R. And so here this quantity delta R summarizes all loop corrections that you get in the model. When you parameterize the leading order by these on-shell parameters. And of course, you can calculate it by self-energy vertex box diagrams and also renormalization counter terms. And so then you can invert the relationship for the W mass and you get a prediction of the W mass in terms of the Z mass, fine structure constant, Muon-decay constant, and delta R. And remember that solving this is not so trivial because it's a quadratic equation, since the weak mixing angle as W square also depends on the W and the Z mass. And so one does this iteratively. All right, so that is the basic thing. And of course, one can now in standard ways compute delta R, but let's analyze the leading contributions to delta R. The leading effects are very well known. So one effect comes from delta alpha, the shift of the fine structure constant. And in the on-shell calculation, this arises via renormalization. So one has charge renormalization and the counter term delta ZE. This gives rise to delta alpha, and it depends on large logarithms from the light fermion masses divided by the W mass. So here, the light leptons and the light quarks enter divided by the W mass, and this gives rise to a large shift in delta alpha, which is a physical effect and which is part of the W mass prediction in the standard model. The second important effect is the shift of the rho parameter, delta rho, which is proportional to the T parameter. And this arises here in this calculation via the renormalization of the weak mixing angle, delta SW square, since the weak mixing angle was just defined as this abbreviation of the mass ratio. Therefore, its renormalization gives you delta rho, and that depends on the top mass square divided by the W mass square. So there is an enhancement from the top mass, or more physically speaking, from the breaking of custodial symmetry. And numerically, the delta alpha amounts to 6%, the delta rho effect minus 3%, and all the remaining stuff from one loop and two loop and higher contributions is around 1%. So delta alpha and delta rho are really the leading effects. And so currently, the full two-loop calculation in the full electroweak standard model is available by those people mentioned here, and also leading 3 and even 4-loop effects are available as well. So let us go on. So historically, before doing the two-loop calculation, there was an important insight, namely when only one-loop calculations were available, people discovered how one can, let's say, combine different one-loop elements to resum and to obtain already very important two-loop effects, namely by taking the one-loop delta alpha and delta rho and delta R remainder and combining them in the way written here in green. You generate by those fractions, you generate two-loop terms, and they proved here in that paper that the two-loop terms of the order delta alpha square, delta alpha, delta rho, and so on, they are correct. So if you would do a full two-loop calculation with actual two-loop diagrams, then those quantities wouldn't change any further. And so delta alpha square is a big effect. So delta alpha is 6%. Delta alpha square is then much bigger than 1 per mil. So this is many, many sigma in terms of the experimental precision. So it was an important discovery that one could resum such effects in this way. Nowadays, we have the full two-loop calculation, and therefore it is not so efficient anymore to do this resummation, but nevertheless, before the two-loop calculation was available, this was very important. Okay, but for us, it's also important to look how one can write this, namely, this resummation is equivalent to writing the on-shell prediction for the W mass in this alternative way here in the box. So instead of alpha at low energies, one can write alpha at mz. And instead of the weak mixing angle defined via the mass ratio, one can write 1 minus mw square over rho times mz square. And with the definitions you see here in the bottom. And so the second way of writing the muon-decay constant reproduces exactly that resummation from Consoli-Holliger-Gallena. And therefore, this is an interesting way to write the on-shell calculation, as long as you have only one loop available. Okay, and so this second way of writing it, of course, absorbs these leading effects from the large logarithms of light fermion masses and from the top mass enhancement in delta rho. Now let's look at the MSbar scheme, which is an alternative way to do the standard model calculation. So first of all, when I say MSbar, here I always mean MSbar with the MSbar renormalization scale mu set to the Z mass, which is appropriate for these electroweak standard model calculations. And the advantage of MSbar minimal subtraction is, of course, always that the prescription for counter terms and for renormalization is very simple and very straightforward, and also, for example, very model independent and easy to generalize from the standard model to BSM scenarios. But the disadvantage of all MSbar schemes is that the MSbar parameters are not observables. So therefore, you have an obscured relationship to observables, and you always need to ask yourself, how can I relate an MSbar input parameter to measurable quantities? And so this complicates the discussion. But nevertheless, the MSbar scheme is particularly efficient here for the muon-decay calculation, because it was discovered that it gives rise to the same resummation of these leading effects that I just explained. So in the MSbar scheme, in this electroweak calculation, you do the following. So the input parameters are defined like this. So you have alpha hat and S hat, which is the weak mixing angle and the fine structure constant in the MSbar scheme. And they are now defined via the MSbar electroweak gauge couplings G1, G2 of the electroweak standard model. And in particular, the weak mixing angle is not defined via pole masses anymore, but also via MSbar gauge couplings. But in the calculation, you also use at the same time the pole masses for MW and MZ. And so in this way, actually, it's not really a full MSbar scheme. It is really a mixed scheme. That would be the better way to call it. It's a mixed scheme. And so the relationship that one writes down in that scheme is G mu, the Fermi constant, is given by the usual tree-level relation. But now the alpha is the MSbar alpha hat at the Z mass scale. The W mass is the pole mass of the W, and the weak mixing angle S is the MSbar weak mixing angle in the standard model. And then you have the loop correction 1 plus delta R hat W in that notation, which summarizes the loop corrections to this relation. And so, as I said, it's important in the MSbar approach to know what is the relationship between your MSbar quantities and measurable input parameters. And here there is such a relationship. So alpha hat in the MSbar scheme is related to alpha in atomic physics by this relationship with a quantity delta alpha hat, which comes from renormalization. And the weak mixing angle S hat and equivalently the rho parameter rho hat in the MSbar scheme can be related to the pole masses of the W and Z mass and can be calculated from the on-shell counter terms delta MW and delta MZ. So everything here is precisely known and calculable. Okay, so this is again the same MSbar relation. And what you are probably able to see is that the form of this is exactly the same as this resummed form in the on-shell scheme. So the alpha hat contains the same resummed large logarithms of the light fermion mass as the alpha at MZ in the on-shell scheme. And the rho hat contains the same top enhanced terms coming from custodial symmetry breaking as the delta rho in the on-shell scheme. But the advantage of the MSbar scheme is now that here, this is not an unnatural, let's say, observation that you can trickily resum some terms, but this is the natural setup of the MSbar approach. And so here you have a systematic way to go on to do two loop calculations of all these different quantities, but still retain this resum form. And that insight, of course, gives rise to the hope that ultimately maybe the MSbar scheme could give rise to an even more precise evaluation of the standard model prediction of the W boson mass. Anyway, nevertheless, the status of on-shell and MSbar nowadays is basically the same. So full two loop is available, plus the same leading 3-loop and 4-loop computations are available. But so we have two state-of-the-art predictions in the standard model available using these two schemes. Okay, so therefore the current status in the standard model is the following. So here I collect some definitions which are only there in case you ask me. But the remark, would be the following. So first of all, what are the physical reasons why we have these two big effects and only those two big effects? First of all, we get large logarithms between the light fermion masses and the W mass because we are relating here low energy observables like alpha and the muon-decay constant to high energy quantities, namely the W pole mass and the Z boson pole mass. And because of this, it's clear that from QED running below the W mass, we get these large logs, and they could be resummed, of course, using QED renormalization group. On the other hand, as you know, of course, there is a breaking of custodial symmetry from the top-bottom mass splitting, and this gives rise to the top mass square enhanced effects in the rho parameter. These are the two big effects. Okay, and so here you see a collection of numbers coming from, on the one hand, the paper by De Grassi et al. On the MSbar calculation, and also an update from us where we plug in current numbers into the formulas. And you see the numbers range here from 80.351 to 80.363. So there is a spread of around 10 MeV, but the quoted uncertainties of all these individual calculations is around plus minus 3 or 4 MeV. So the accuracy of the standard model prediction is very high and actually a little bit higher than the experimental one. So much for the standard model review. Now let me discuss the BSM calculations and the problem that has appeared. And let's begin with a small overview of BSM scenarios. So of course, typically the dominant contributions in concrete BSM models arise via delta rho or the T parameter, as we also heard in previous talks, and well-known examples which are also now often discussed after the CTF measurement are models with Higgs triplets, because the Higgs triplet, if it has a vacuum expectation value, gives even a 3-level shift to delta rho. The 2 Higgs doublet model can easily give rise to significant corrections in the rho parameter. SUSY with stops bottom loops, but also Giorgino and Slepton loops can give rise to breaking of custodial symmetry and big effects in delta rho. Also, 4th generation models could in principle give rise to large contributions, but in that case, they are anyway already excluded by LHC data. Okay, but in general, what is very important to know is that, of course, if universally new physics becomes heavy, EFT arguments tell us that BSM decouples, and the prediction of BSM for the W mass should converge to the standard model prediction in the standard model mass. In particular, very clearly, if BSM physics is heavy, there can be no change of the QED running between the light fermion masses and the W mass. And so there cannot be a change in these large logarithms coming from QED running, but the main effect comes from delta rho. Okay, and so here, just to flash also once again this plot, we have seen it already in Emanuele's talk as well. So in concrete BSM scenarios like the MSSM, it is of course possible to sit down for a number of years and to do also 2-loop calculations. And so here in the distant past, we have done a 2-loop calculation of delta rho in the MSSM, giving rise to that plot and also to its update. That update on the right is taken from a talk by Sven Heinemeyer from recently. They somehow changed the color code. But anyway, this calculation was done in the on-shell scheme for the MSSM, including 2-loop effects in delta rho. Similarly, in another study by Hessenberger and Hollig, they did a full 1-loop plus 2-loop delta rho calculation in the 2x doublet model. So generally, in such concrete, well-motivated models, this effort is possible, and it has been done in the literature. But now our question was how to do a general calculation which is valid for as many models as possible in generic spectrum generators. How can we implement this calculation of the W mass, in particular in FlexibleSUSY? And so here in that context of spectrum generators, the MSbar scheme looks extremely natural, because spectrum generators typically apply the MSbar scheme anyway, because they want to do renormalization group running between different scales, between BSM scales and electroweak scale, maybe even running up to the gut scale, depending on the model you are looking at. And so the MSbar scheme is a natural scheme which is present in all these spectrum codes anyway. And so the MSbar scheme was applied in many calculations, also in this famous loop calculation paper in supersymmetry, but also in well-known programs like SoftSUSY, Spheno, and also in FlexibleSUSY. But in the MSbar scheme, there is a problem, namely this non-decoupling problem. And honestly speaking, in hindsight, it looks extremely obvious that the problem is there, but somehow people didn't really notice it. Also, we didn't notice it initially, to be perfectly honest with you. And the problem was obscured, first of all, because people in, let's say, the 1990s were looking at rather light spectra of new physics particles and not at very heavy new physics. And also, technically, there was a compensating bug in some of the programs which really canceled the effect coming from the non-decoupling. And so also it was not really observable in plots. So here is again the formula of the MSbar approach to the Muon-decay and the W mass, where we have the MSbar alpha hat fine structure constant and the MSbar weak mixing angle S hat. Okay, and this formula was excellent in the standard model because it resums these two large effects from delta rho and also from the QED running and the light fermion masses. And now the point is that this relies completely on the fact that in the standard model, you really have only two physical scales. You have the W mass scale, the electroweak scale, and the light scale. But in BSM models, you have a third scale, namely the heavy BSM masses, which might be much heavier than the W mass. And so therefore, the structure of scale hierarchies changes. And this means that this MSbar approach now becomes problematic. So technically, in this delta alpha hat, the MSbar fine structure constant, there appear the large logs from the light fermion masses, and they are really physical logs which must be present in the physical prediction for the W mass. But you will also get large logs from BSM heavy masses divided by the W mass, and those logs are unphysical. They must drop out from the final calculation. And however, they are present in this alpha hat fine structure constant. Therefore, this is a fake effect which must cancel among all the different elements here, building blocks of the calculation. On the other hand, of course, new BSM contributions to the rho parameter, they can be present, they are physical and very important. Okay, and so that gives rise to a problem. And let me just show you here a plot which illustrates the plot problem. That is a very nice paper by Philipp Diesner and Georg Weiglein. So Philipp Diesner was a long-term collaborator of us also on MRSSM physics. And then they also analyzed this difficulty here and produced this plot, which is a plot in the MRSSM prediction for the W boson mass. And they carried out a one-loop on-shell calculation, which is the black line. And you see the black line really converges very nicely to some value, which is the standard model prediction, if the new physics masses become heavy. But you also see two different MSbar type calculations from spectrum generators, namely the blue dashed line and the pink dashed line. And both of those show non-decoupling, because you see, as the new physics masses increase, the dashed lines just go away continuously from the standard model prediction. And this is the non-decoupling, which is unphysical. And so this is a fake, incorrect prediction here of those two spectrum generators. And what I mentioned before is that there was somehow a bug in early versions of the spectrum generator, which gave rise to another incorrect two-loop term. And this incorrect two-loop term meant that the blue dashed line is numerically very close to the standard model prediction and very close to the on-shell result, and therefore the problem was not really apparent. But after correcting that bug, we got the pink line, which is really far away from the standard model prediction, also far away from the experiment by many sigmas. And that difference between the pink line and the black line, this is really due to this non-decoupling effect from fake large logs coming, for example, from delta alpha. And numerically, this effect amounts to about 100 MeV. So this is more than 1 per mil, many sigmas. And so formally, I can tell you where it comes from. So in the MSbar scheme, you have this kind of contributions, neglecting many other things. You have 1 divided by 1 minus delta alpha hat times 1 plus delta RW hat. And all of this might be evaluated at the one loop level. So if you evaluate it at the one loop level, and in the numerical code, you get whatever you get, but analytically, you can check what actually it means. If you expand the fraction, you get a 1 plus delta alpha hat plus delta RW hat at the one loop level, plus delta alpha hat squared, and so on, plus some other terms. And so if you do everything correctly at the one loop level, then among all these one loop terms, the non-decoupling large logs, they cancel analytically exactly. And then at the one loop level, you have no problem at all. But you get delta alpha hat square effects. This is a two-loop expression, which is part of your numerical evaluation. But since you do not do a full two-loop calculation, these delta alpha hat square logs are not cancelled by all the other two-loop terms, which would be there in a full two-loop calculation. And therefore, numerically, you pick up those the square of those fake large logs at the two-loop level. Okay, and how large is that? So, for example, delta alpha hat from new physics can be easily 3%. And so the square of 3% is around 1 per mil. And so in that way, you immediately understand why it can be really true that this pink line in the plot deviates by 1 per mil from the black line because of those fake incorrect two-loop terms picked up from the MSbar scheme. That is the problem. And so how to avoid the problem? In some sense, very simple. And basically that's also what other speakers have done in their approaches automatically. But the question for us was what to do in the spectrum generator FlexibleSUSY. So this is a spectrum generator, a program where you have an input model file defining your theory, like MSSM, NMSSM, MRSSM, and so on. Non-SUSY models exist as well. And then the code should give you precise computations, not only of the spectrum, but also of observables, like the Higgs mass, like G-2 of the muon, but Higgs decays, but also of the W boson mass. Okay, and so our approach is now very simple after understanding all of this. What we should do is to take the standard model contributions fully into account, including all the available two-loop entire corrections from the literature. But for the BSM effects, we should not do this resummation, but we should strictly expand the MSbar formula to precisely one loop order in the BSM effects, because then we know the non-decoupling cancels. We have taken into account the big effects from the standard model exactly, and the smaller effects from new physics taken into account at basically leading order, which is typically sufficient. And then we arrive at the following formula, namely the W mass in the BSM model is given by the standard model prediction coming from the Technische et al. Prediction times 1 plus a correction, and the correction is given by this one-line formula, which involves these elements, namely a tree-level shift in the rho parameter, which is existing, for example, in Higgs triplet models, then the one-loop delta rho shift, the one-loop delta R hat W coming from all the box diagrams and vertex corrections and so on, and the delta alpha hat coming from the shift of the fine structure constant. This is the formula, and with this we get a prediction which works and has all the nice features that we want. And so let me just illustrate this with a case of the MRSSM. So a few words on the MRSSM. It is of course not such a very well-known model, but maybe it deserves a little bit of attention. It is an alternative realization of supersymmetry, which is different from the MSSM. And you might actually argue that the MRSSM is even simpler than the MSSM. It contains a new symmetry, namely a continuous R-symmetry, where the SUSY theta variables undergo a U1 phase transformation, and all the superfields are assigned some charge under this U1 symmetry. And then the phenomenological impact of that is the following. So there is no left-right mixing anymore between squarks or leptons, because the left-handed squarks and right-handed squarks have different R charges, so they cannot mix anymore, which kills a lot of parameters of the MSSM and a lot of sources of flavor violation, for example. And also Majorana masses for all the gauginos and also the Higgs-inos are forbidden as well, again because of this R charge. And so because of that, we need to have Dirac masses of the gauginos and the Higgs-inos, and that involves that the MRSSM has new superfields compared to the MSSM. It has a superfield which give rise to the Dirac partners of all the gaugino and Higgs-ino masses. And so from that point of view, the MRSSM has more field content, a higher number of degrees of freedom, higher number of particles, but it has a higher symmetry, and therefore it has less free parameters than the MSSM. So depending on how you look at it, it's either simpler or more complicated than the MSSM. But anyway, it's a very predictive supersymmetric scenario, which is distinct from the MSSM because of this different field content. And so for us, for the W mass, it's particularly interesting because this Dirac partner of the SU2 gauge boson is now a triplet superfield. It's a triplet superfield which contains in particular a triplet scalar, in other words, a Higgs triplet. So a Higgs triplet is automatic part of this MRSSM, and automatically from the potential, it can have a vacuum expectation value, and in this way, we would automatically get a tree-level contribution to the rho parameter, and therefore a tree-level shift in the mass of the W boson. On the other hand, there are all these triplet partners to the, Dirac partners to the Higgs-inos. They are new superfields and called R here. And out of those superfields, we can obtain superpotential terms. And the superpotential terms, which are gauge invariant in red here, have so-called lambda prefactors. And they have a structure like Higgs doublet times triplet superfield times the new Higgs-ino superfield. So the structure of these new lambda terms in the superpotential is basically the same as the Yukawa coupling of the top quark. So if you compare it, in gray is the top Yukawa coupling. You have Higgs doublet times top quark doublet times top quark singlet. And that is the same structure as the lambdas, where we have Higgs doublet times two other superfields. And so the impact of the lambda parameters is in many ways very similar to the impact of the top Yukawa coupling in phenomenology. So this impact is similar, for example, in the case of the Higgs mass calculations. So many of you might know that supersymmetry also allows predictions of the Higgs masses. They depend very strongly on the top mass and the top Yukawa coupling. So here there is a similar influence of the lambda parameters on the Higgs masses. And of course, also the top Yukawa coupling is the source of the rho parameter shift in the standard model. And so the same would be true here for the lambda parameters as well. So this MRSSM by construction has two interesting sources which give rise to shifts in the W mass, Higgs triplet and the lambda parameters. And so here are the two formulas. So the Higgs triplet vacuum expectation value shifts the rho parameter by this ratio of the Higgs triplet wave to the normal doublet waves. So the shift must be phenomenologically small. So typically this implies an upper limit on the magnitude of the Higgs triplet, but now in order to accommodate the CTF measurement, a very small but non-zero triplet wave could easily do it. Similarly, the impact of the lambda parameters on the T parameter or delta rho is similar to the top Yukawa impact. So we have here terms which go like lambda to the fourth power times some prefactors. All right, and because of that, we get the following prediction. So first of all, on the left, I want to show you that this decoupling, which was the core of the theoretical discussion, this decoupling works. And so here we have the prediction of the Diesner-Weiglein paper in the dotted line once again. And the FlexibleSUSY prediction now nicely converges against this on-shell prediction. And so there is no asymptotic limit here because the plot is a little bit more complicated because while varying the SUSY masses here in the plot, also the Higgs boson mass changes as a function of the SUSY masses. And therefore, we compare here to a standard model prediction with a varying Higgs mass. And therefore, the standard model prediction itself is not a constant here in the plot. And therefore, we do not expect an asymptotic flat limit, but such a convergence between all the different curves. And that is what we observe. So decoupling works. And on the other hand, on the right, you see a phenomenological evaluation of the MRSSM. And you see here in the contours for the Higgs boson mass prediction in the MRSSM. And so the Higgs mass depends very sensitively on this lambda parameter, which you have here on the y-axis. And so for large lambda values, like 1.7 here or minus 1.7, you get a Higgs mass of 125, which agrees with the experimental measurement of the Higgs boson mass, which is nice. And in the colored contours, obviously, you have a prediction of the W boson mass. And you see that, again, for large lambdas, you get large contributions to the W mass. Which compensate the decoupling that you have. So on the other hand, of course, the larger the SUSY mass is, the smaller the contribution to the W mass. But if the SUSY masses are like here in the example, 750 GeV, and you have the lambda, which explains the Higgs mass minus 1.7, you are in agreement with the CTF value of the W boson mass measurement. So this is possible in the MRSSM. All right, that brings me to the conclusions. So in this talk, I spent a long time on reviewing the standard model theory prediction, which is, of course, a very old subject. And the situation is very well advanced and in very good shape. So we have reviewed the on-shell and the MSbar predictions. They are available at the two-loop level and beyond. The uncertainties are ±3, and the different calculations differ from each other by up to around 10 MeV, but the status is very stable. For the BSM predictions, there was this tricky subtlety of the non-decoupling effect if we just naively apply the MSbar scheme, which would be the most natural thing to do in spectrum generators. But we can avoid the non-decoupling issue by implementing it in the way I described it. So for the MRSSM, I can say again, the MRSSM is an interesting scenario. It's, one could say, a minimal implementation of supersymmetry, which is distinct from the MSSM. It has a lot of interesting phenomenological advantages. For example, automatic agreement or more or less automatic agreement with flavor physics constraints, more automatic than in the MSSM. It has interesting additional contributions to the Higgs mass and to the W boson mass, which makes it nicely able to accommodate all the observed measurements. In other studies, we also showed that the LHC limits on the quarks and gluinos are actually a little bit less strict than in the MSSM, which also brings down the experimental limits and opens up the parameter space a little bit more. Maybe just to end the talk with a side comment, I didn't talk about it, but of course there is not only the W mass, which is interesting, but there is also G-2, and I'm very much interested in G-2 of the muon as well. So the MRSSM is not the best possibility to explain the G-2 value. It might work in extreme corners of parameter space, but if G-2 persists with this current 4 sigma deviation, then the MRSSM is maybe not the best candidate for explanations. And then the question would, of course, be which models can accommodate G-2 and the W mass and all the other measurements. But that is the question for a different talk. So here I want to stop. Thank you very much for your attention.
Okay, thank you very much.
Dominik, thank you for your nice talk. What do you mean by MSUSY?
So MSUSY stands simply for the universal mass of all the supersymmetric particles. So in this plot here, in both plots, in fact, we have set most of the SUSY particle masses to a common scale, which we called MSUSY, and then we vary the scale. And so that is the simplest way to study the model, of course. And clearly, one could go to more complicated scenarios. But in order to illustrate the basic features of the model, we use this simple approach.
So you assumed all the SUSY particles have the same mass called MSUSY.
Yes,
right?
Yes.
Okay.
And so for this reason, of course, there are strong LHC constraints on the quarks of the first and second generation, which would be given by this MSUSY. And so we didn't plot the LHC constraints on the masses here in the plot. But that is why we ended up at this high value for MSUSY of 750 GeV, where the LHC limits are evaded for the gluinos and quarks. But actually, the gluinos and the first 2 generations quarks are not important for this analysis here. So, of course, one could also relax the analysis and say those strongly interacting particles are heavier than the leptons and heavier than the particles affected by these lambda couplings. And then one might explain also the W boson mass and the Higgs boson mass in a way where some SUSY particles are a little bit lighter than 750 GeV. So you see in the plot that also, let's say, 1 TeV masses could work for the W boson mass, but then one would need a split spectrum where at least some particles are heavy and above the LHC limits.
Okay, thank you.
Other questions or comments? Let me ask a naive question. Could you go to page 16?
Okay.
Okay, so here possible log of MSBSM divided by MW in delta alpha hat would be unphysical. And is it because here we need alpha hat defined in the standard model, not in the full theory, namely the BSM?
Yes. So what is behind this statement is, of course, what do you express as a function of what? So here we express the muon-decay rate and the W boson pole mass in terms of other physical quantities. And so in the physical relationship between the W mass and these low energy quantities and the measured alpha at low energies, in this relationship, it is clear from the beginning that such large logs cannot appear. But of course, if you, let's say, want to know what is the relationship between the muon-decay or between the W boson pole mass and some running parameters at a high scale in your BSM theory, then that relationship will involve large logs. And so clearly, if you have, for example, a fundamental theory, the MSSM, and the MSSM particles are 2 TeV in mass, and you are asking yourself, I have the MSSM spectrum and the running MSSM parameters all defined at a 2 TeV mass scale. What is the relationship between those parameters and the muon-decay rate, or between those parameters and the W pole mass? Then that relationship will involve such large logs. And so in one of the previous talks, unfortunately, too early for me, but there was the running in EFTs above the W mass. And so for sure, those logs could be resummed in terms of an EFT approach. And the meaning of it would be, what is the relationship between the fundamental high scale parameters and the observable W mass? That relationship will involve large logs. But you have to remember that these high scale running parameters in the fundamental theory are not directly observable. You have to relate them to observable quantities like alpha equal 1/137 coming from atomic physics. And that relationship involves also loop corrections and involves also large logarithms and so on. And once you express the W mass as a function of measured quantities at a low scale, then those blue logs must drop out. And so that was also the point. So if you really aim for a precise prediction of the W boson mass in terms of spectrum generators like FlexibleSUSY, this high precision, at least we found, was not really achievable if we stay in this paradigm that we have a fundamental theory which is defined by running couplings at a high fundamental energy scale, and we predict all quantities in a systematic way from those parameters. Of course, that is technically possible, but the uncertainty, the theory uncertainty you pick up in this way is way too large. Of course, you know, in FlexibleSUSY, we are also predicting things like SUSY masses, and we do one loop predictions of Giorgino pole masses and squark and lepton pole masses and all this sort of stuff. And this is done starting from the MSbar scheme at the high scale. And so for those masses, we achieve maybe a 1% precision, and that is good enough. But for the W boson mass, 1% precision is, of course, not good enough. We need even much better than per mil level precision, and therefore this starting point in the spectrum generators from the high scale, predicting systematically using loop calculations the low energy W pole mass is just not precise enough. So we had to restructure the approach for the W mass calculation and really write the prediction of the W pole mass as a function of observable low energy quantities, eliminating as much as possible those high scale BSM effects. And that is really the core of the issue. I hope my answer was not too convoluted.
Okay, thank you. Are there other questions or comments? Okay, if there are no more questions, then
May I add something?
Of course.
I would like to add something. Yeah, hi, Dominik. So, sorry.
Hi.
I just was wondering if your code could be tweaked to include like the case of two Higgs double models.
The two Higgs doublet model is already available.
Oh,
So
okay.
the two Higgs doublet model, so this FlexibleSUSY, despite the name, is also able to treat non-supersymmetric models. And the two Higgs doublet model is, of course, one of the prime candidates for a non-SUSY model. And so we have versions of FlexibleSUSY, or basically those model files which define FlexibleSUSY for the two Higgs doublet model. That already exists.
Oh,
For this
great.
project, we have not really focused on the two Higgs doublet model and done examples for it, but it is definitely possible. That is the goal also.
Okay, thank you very much. I will look at it.
Yep.
Thank you. Bye.
Other questions or comments? Okay, otherwise, let's thank Dominik again. Thank you.
Thank you also.
Okay, is there any
Okay, thanks and bye-bye.
concluding remark or something?
Just thank you very much. I mean, I thank all the speakers for very nice presentations. And we have to see what will happen eventually from the experimental side, right? So anyway, thank you very much for your nice presentations. Bye bye, and have a nice day. Bye bye. Thank you.
Thank you. Thank you. Bye bye. Have a nice day.
Bye and thanks.